Airjet, or Vortex spinning, first appeared for production use in the early 80s. Early versions of the spinning method were only able to spin synthetic yarns with long staple lengths, but research and development has allowed it to spin shorter fibers and thus 100% cotton yarns. The popular end-use market tends to be for sheeting, print cloth, fleece, and other garments which need to be low pilling. Rotor spinning is about 10 times faster than ring spinning. Airjet spinning is twice as fast as rotor spinning, or 20 times faster than ring. This speed is consistent no matter the yarn count being produced. Airjet spinning is more effective at finer yarn counts between 40 single and 60 single number English, but struggles at counts coarser than 12 single number English. Airjet spun yarns tend to have lower tenacity than ring spun yarns, but higher resistance to abrasion and pilling. The amount of hairiness can be tightly controlled by the machine. Short fibers are removed during this spinning process, resulting in a waste percentage between 3 and 8%. This spinning system uses sliver as its input, thereby taking advantage of the cost savings afforded by removing the roving step required by ring spinning. Much like rotor spinning, it also produces a wound package that is ready for subsequent use in weaving or knitting. This negates the need for a separate winding step. The Airjet machine uses roller drafting as the means for reducing linear mass in the fed sliver. The drafting system is not unlike the drafting system configuration found on the ring spinning system. After exiting the front pair of drafting rolls, the fiber is pulled into an orifice by a suction airflow created by the vortex that will perform the twist insertion. As the fiber enters the vortex zone, it is literally spun into a yarn structure by the whirling air currents. Like rotor spinning, there is some degree of random fiber entanglement that is also involved. This is the main reason for the somewhat lower yarn strengths of Airjet yarns when compared with their ring-spun counterparts. This results in a mostly parallel core of fibers surrounded by tightly wound wrapper fibers, causing a smooth surface to the yarn. The wrapper fibers are most often twisted in the Z direction, but the equipment can be set up to produce S-twist when required. Just as in rotor spinning, this process is highly automated with automatic piecing of broken ends and automatic doffing removal of full yarn packages.